answering questions. Okay, so I'm recording now. Also FYI. Okay, so we will start with just some ethers and epoxides. And these are just I didn't put the question on here, but it just says provide the missing reagents / conditions or major organic products as appropriate. Obviously, you'll see as we go. And then pay attention to stereochemistry and include racemic mixtures unless specified. Yeah. So this first one is we have an ether. And with this one, we have excess. Did you guys see that line I just made? I just want to make sure my internet's also working.
Yeah.
Okay, cool. This one is an excess, so that just means that it's going to happen like all the way through. It's not gonna, if you have one equivalent, it'll only happen one time, whereas in excess, it'll happen until it can't happen anymore. So for this one, right, so we can break our bonds right here. What happens with something like this is we will have, for this, we have like HBr, right? But like you would have this just as like a little reminder of what happens if you have like excess of something, right? Sometimes we do this too, HBr. That should be lowercase. Sorry, guys. Excess of it. And then so what would end up happening is you would have your RBr. And remember, like R just means like whatever is this hydrocarbon on this side, and this like R prime is just this hydrocarbon on this side, right? So that's all that means. Plus you're gonna have your water. And then because your oxygen here is gonna pick up these hydrogen here, and then your bromines are gonna go on these sides, on these carbons over here. This is a methyl group here, right? So, and then in this case, in your prime, right? So that's all that happens when you have like an excess of like whatever the acid is, right? But in this case, HBr. So when you have it in excess, so for this one, it's just, remember, these are just like predict the products. So I always say count your carbons to make sure that you don't lose them. 1, 2, 3. Dr. Fly will tell you the same thing because I always lost my carbons. So there's my 1, 2, 3, and then I just add my Br to that. And then you can put your H2O, but you don't have to, right? It's assumed. It's an assumed side product, so you don't have to do that. And then this last one is going to be you could do Br like that, or you could do, Br methyl or something. But, so this is just like your predict the product, right? So pretty straightforward. Does anybody have any questions about that so far?
No.
Okay, cool. And then, so for this, again, we have HBr. It doesn't say in excess, but when we're breaking the bonds to the oxygen, we have these two bonds here, right? But remember that you're not going to have SN1 or SN2. There's no substitution reactions here at this sp2 hybridized carbon. So we're not going to have a bond breaking on that side. We're only going to have a bond breaking on this side. So then what you end up getting is you have your phenyl ring here, right? And then you will still have your oxygen that will pick up the hydrogen now. And then on this side, 1, 2, 1, 2, plus your bromine, right? Any questions there?
If it was excess, would they both be bromine then, or would it still be oxygen and bromine?
No, you're still gonna have your alcohol there. The excess doesn't really have anything to do with it. You could still have excess here, and it still wouldn't do anything because it's not going to happen at this sp2 hybridized carbon.
Okay.
Remember that SN2, like substitution reactions, don't happen on sp2 hybridized. So that's why. So this will just be, yeah, so it'll just break that bond there. And then for this one, we're getting, we're going from an alkene to an epoxide. And so there's a few major reactions that like do that. One of them, I don't know if you may or may not have seen, but anyway, does anybody remember what the major reagents are that turn an alkene into an epoxide?
Is it MCPBA?
Yep.
Okay.
MCPBA is one of them. And then I don't know if you guys have seen the other one. Does anybody remember a second one?
No, I don't.
It's the per acid. So it's the RCOOOH. This also makes an epoxide. It literally just, it's basically a carboxylic acid with an extra oxygen in it. 1, 2 here and right here, and then an oxygen here. So that's what it looks like. But this will also make an epoxide from a alkene. But yeah, I assume so, but does she have like similar questions like this where it's like you're given a product and the reagent, or like a reactant and a reagent and you have to predict the product, or like you're given the reactant and the product and you have to predict the reagent? Does she have similar questions like that on the exams?
Um, yes, kind of. Like there was some of the drop down ones. I know
Yeah,
with
the
collab,
drop down, yeah.
there was more of like drawing the predict the product ones. Like for hers, there's only been like 3 response questions, but they've all been like synthesis, like longer response
Yeah,
ones.
yeah. At this point, probably most of your free responses are going to be synthesis. These would typically be like drop down questions
Okay.
or multiple choice ones. But you guys are seeing these. I actually haven't looked at any of her exams. I have looked at like a few questions here or there, but I haven't like examined them. So I didn't know if these are like things that like you guys are actually seeing, where you're like getting kind of questions like this and you have to like predict whatever's going on.
I mean, like the exam is still like you can't see what you got wrong. So
Yeah, no, I know she doesn't release them. Mostly
yeah.
because like she's supposed to be releasing them on Wednesdays. But when
No,
you're
but
doing,
even like the first week's exam, like you can't see, like you see your score, but she doesn't like show you which ones you missed.
oh, it's like still muted, like the answers are muted
Yeah.
still.
So like you
Got it.
can't, so it's like,
You might be able to like if you email her, you can ask her. She might like be willing to like meet with you and go over them. Some professors do that where they won't like show you the missed questions, but if you meet with them, they'll go over them with you, but they don't actually like release them for you to see on your own. So
okay, weird. Okay.
it's yeah, she's not the only professor. That I have a couple other professors that I've taken that do that. And it's mostly just so people don't like upload stuff online or whatever, like tell other people. And sometimes like your exams will be muted until like later on in the week. Like you can't even see what your score is because a lot of those things have to do with like preventing people from cheating. So like if you took an exam and you knew and you got a 100 or you got a 98 or something like that, and you could tell somebody what the answers are because you know that you got a majority of the questions right. You know what I mean? So like that's what a lot of that stuff is. But I definitely encourage everybody to just like reach out if you have questions about your exam and you want to go over it. Don't like, and if she doesn't email you back right away, like keep bugging her about it. This class will go obviously by pretty quickly and concepts build. So don't let yourself like fall behind. And if you're still having issues, like email me. I think the other TA that only does grading of the exams is also in your Canvas. You can like email her through the email thing. So if you do want to go over previous exams and you can't see them, just email people. Because you should be able to see those. You should at least be able to like go over what you got wrong. So
Okay.
Okay, yeah. So yeah. All right. So then this one, so do you guys remember when you see like epoxides and you're doing reactions, what you want to look for to like figure out what's going on, especially for like your synthesis problems? Do you guys remember?
No.
No.
Like acidic versus basic conditions?
Oh
Oh,
yeah.
You guys remember that? Okay, so what happens in an acidic condition?
it attaches to the most substituted carbon.
Yeah, also that, but before we even get there,
You protonate it.
yes, you got to protonate first. So acidic conditions means that you have extra protons, right? Like, so you want to protonate first. So with this, you know, you have your this here, and here's your proton. You'll come and you'll protonate, and what'll happen is, let me make this a little bit thinner so you guys can actually see this. So what'll happen is then you still have your epoxide. I always do this, and then I'm like, I don't have anywhere to put my oxygen. Anyway, so remember that epoxides are strained, right? So they're like already having issues. They're already having electron strain issues, and then we're putting this positive charge on here as well. We're gonna keep the stereochemistry, right? I'm gonna zoom out a little bit so y'all can see this. So we're gonna keep the stereochemistry on this. And so this is like pretty important to remember, right? To just keep your molecule looking similar, especially when you like have a lot of this stuff going on, right? So we've protonated, and then we have our OET that's coming in, and like Norman said, it's going to attack the most substituted carbon, so it's going to come in here, right? And then what's going to happen is these electrons are going to kick off here, and oxygen is like, oh, thank God, because I hate being a cation. And then so what we have, and this is our Lewis base, Lewis acid, right? Remember to write that. Don't forget, I have lost points for forgetting to do that, so always remember to do those. And then so now we're gonna keep the stereochemistry, right? So we have our OH, and we've got this carbon here, right? We've got a carbon right here, so that's this one. And then we've got this carbon here. Let's just move this. We're keeping our stereochemistry, right? So we're just moving that up there. We're keeping our methyl on the wedge. And then we're just adding this OET in here, right? So OET. And then we have, again, our positive charge here. And so then what happens is, like any good catalyst, right? This is going to regenerate itself. This hydrogen is going to get picked up by another OET, right? That's what's happening, although you guys don't necessarily have to know that, but this is like picking up this other one. So that's how this kind of like disappears and kicks off. And then what we have left is, again, making sure to keep our stereochemistry. And there's our alcohol, and there's our OET, right? Anybody have any questions on that?
With this, if we're doing this, do we have to show like all of the little like the OET stuff at the bottom?
If they're asking for synthesis, yes. If this is just asking you to predict the product, you can just literally draw this. I'm showing you this so that way you know what's going on.
Yeah, okay.
Yeah.
Okay.
But because this is like predict the product, you can just literally look at like this product and this reagent and draw this structure. And you should get it correct.
Yeah.
And if it's a drop down, then, or if it's like a multiple choice, like choose the correct,
Yeah.
You're not going to see all that anyway, but I'm just showing you mechanisms so that way y'all can, know what you're doing, because you will see this stuff in synthesis, even if it's not now, you might see it later. So, cool. So we already talked about this. What does this one do?
Makes the epoxide.
Yeah, exactly. Out of what?
The double bond.
Yeah. Yeah, no, all good. Hop in. Everybody can answer at the same time. And then, so if it's epoxide, then that means once you get your epoxide, right? So this makes your epoxide, right? So we have these methyls already. So let's just do this, right? We've got the O there, right? So there's our epoxide. But now we have this step 2, this acid workup step. That's what this is called, right? So we're making an acidic condition. So what ends up happening is now we have these we have this going on, and this is going to take over this, and it's going to make this oxygen pretty happy. And then so we end up getting, I'm gonna run out of room. I draw too big. We'll keep this and we'll keep this, right? And then, oh, whoops. This and this, right? And so now we have this going on. And then so what's gonna happen is, again, we're gonna have a water come in, and it's going to attack in here. I'm drawing this in blue so that way you guys can like actually see what's going on. So you're gonna have this come and attack in here, but this is, remember, this is anti-addition, right? So this is gonna kick off on this side, and I'm saying this so that we can evaluate our stereochemistry. So, and then just in order to not take up space in my other, I'm just gonna go this way with it. And then so what ends up happening is we have this ring, right? And then here's our methyl, and here's our oxygen, our alcohol. And then, so this is the bond that got broken, this one in green here. So this is the one that kicked the electrons, and I'm going to draw them right here, kicked those electrons on there. And then the dash got moved forward. So it's no longer behind and it's in front. And then our alcohol is put on there. Well, okay, what really happens is like you have your, right, whoops.
If we like did the exam and we had like one alcohol on a wedge and one on a dash, but the wedges and the dashes were like not in that exact position, would that be a problem or not really?
So if what you mean, so let me just finish doing this real quick, just so I can show you. No, it's okay. It's okay. I just want to do this just for completion so that way you guys can see this, and then this is going to come on here, and then this is going to become your new product. And then this is obviously plus minus because you could get it either way, right? Like the epoxide could be on either side. So whichever side it ends up going on is whatever side of the product it would be. So it's plus minus. But anyway, but to your question, if what you're saying is instead of this, you had
yeah, exactly. But the OHs are, yeah.
Yeah.
They're still opposite. Is that okay? Because can't they rotate around? Oh, they can't rotate around.
Because yes, but no, but it has to do with like etiquette of drawing. So whatever side you choose your wedges to be on has to be consistent throughout whatever synthesis or drawing that you're doing. So because in this instance, you've chosen, like if we're going in a clockwise direction, you've chosen that your dashes are going to be first and your wedges are going to be second, that means that in this carbon, going in that same direction, then that means that your dashes have to come before your wedges. Does that make sense?
Yeah, but it's not, it doesn't really matter that it's like pointing down, like, because I was just like, when they're dashes, their wedges are together, I didn't know if like you made it point down for a reason.
No, is it like, do you mean like because I have my dashes over here, like, or what do you mean like pointing down?
Okay, so like, how you see the green one, how they're like, those are together?
Over
and then
here?
the next one you separated, yeah, and then you separated them, like where it's like.
Yes, because this is still technically one bond here. This is still one, this is all together. This is the
Yeah, no, I know.
epoxide.
Okay, so when you separated them, you said that it kicks it down, and then you drew that wedge straight down. I didn't know if we just draw it straight down, like when we were drawing the chairs before, where there
No,
was like
this is different. So those are different things. So this is my methyl, and now this is my methyl. So
Oh.
what I'm saying is it pushed this attachment of the water pushes the methyl forward, which is why it now is a wedge,
Oh, so
because
they,
it's anti-addition.
okay, that makes sense. Okay.
Yeah, so that's why. So it's not that this wedge here got pushed downward here, right? This wedge here is a totally different bond.
Okay.
This is the original methyl that we started with back here.
Okay.
That's what this is. So this is an anti-addition, and that's why we have an alcohol on this side and an alcohol on this side. But again, if you get this problem, and this is just a predict the problem, you can go right from this straight to this, right? Because what you would do is you would just know that MCPBA is going to create your epoxide, and then here's your epoxide here, right? And then your acid workup step is going to create your anti-addition of alcohols, right?
Okay.
So this is all just mechanism, right? This is just mechanism to show you what's going on. And this, I can erase this because this doesn't have anything to do with anything. But yeah, so all of that stuff is mechanism. So I'm just showing you what happens so that way, if it comes up, you know what's going on. But you're more than welcome to jump right from here, right from here, start to here, finish.
Okay.
Okay. Yeah, good questions. Okay, what do we have next? Okay, so we talked about this before, right? This was acidic. This is obviously also acidic, but different, right? But so this, what is this? Is this acidic or basic?
Basic.
Yep, exactly. So what does it mean when you have an epoxide in basic conditions?
That's the least substituted carbon gets attacked.
Yeah, exactly. So that means, so of these two carbons, right, our least substituted carbon is going to get the OMe. Remember, this is, right? So we're going to get the OMe over here. It's going to come in here. This is going to pop up here, right? And then what we end up getting is we have MEO, 1, 2, 3, 4, and 5. There we go. Okay. I'm like, wait, where's my other one? Right. Yes. So this carbon here in purple is this carbon here in purple. So anyway, okay, so then we have, so now we have in our basic conditions, right? Because this now we have is reacting with MEOH, is our basic condition. I changed my color. So then what we end up having is it just turns our oxygen, right? Just gives it the hydrogen. So then we have the OMe for alcohol, right? Any issues with that?
No.
Okay, cool. Yeah, so basic, you're like he said, attacking the least substituted carbon, and then you will end up with your alcohol, obviously, on your oxygen, right? Whoops. Okay. Then we have this bad boy. So it comes in steps, right? But what does number 1 do? Just for some review, right? What does this do to this?
Breaks it, and where the H is, it makes it a negative.
Mm-hmm. Yep, exactly. So we end up with H3C. Right? And then what? And then our second step is to add the epoxide. So what happens?
Since it's with the acid workup, would that be the most substituted, or is that not because that's the third step?
It's a third separate step.
So then it would go for the least substituted one, right?
Yes, exactly. So then we would have this, oops. At least substituted, so we'd have it coming and attacking here. So then what we end up with is we have H3C. Oh gosh. I hate when you have like the triple bonds. It's like, where exactly are your carbons? Okay, so one, 2, 3. Okay, 1, 2, and then, sorry guys, I'm running out of room. I write too big is my problem. There. Okay. There we go. Boop, boop. Okay, cool. And then obviously we have the acid workup step, right? So this, right? And then we have the acid workup step for that reason, so that now we have this. I'm just gonna do this. Hopefully that'll be easier for me. That's there. So then we have this, H, that, this. God. Anyway, yeah, so this is our acid workup step, H3O plus, right? So again, we can, this we know is just going to cleave it here so that we can attach this. Because this is basic conditions, we're going to add to the least substituted, right? So we know that this triple bond here is going to attach to this here, which is going to cleave this bond. And so then this ends up turning into, without the triple bond, right, we end up having this situation, right? Because we've broken the epoxide here, right? So that's how we end up having this, right? And then you literally just add your, right? And then we have our acid workup step, you add the H, right? This is our CH3 here. That's what this is. And then our triple bond, and then these, right? Does that make sense? Quick, easy way to, quick down and dirty way to look at it. This one right here. How are we feeling? You guys feel confident with that type of stuff? Like predict the products, know what's going on? You guys sound like you know what's going on.
That one's not my favorite. The other three, just fine. That one, I don't like it.
Oh, this last one? Yeah, I know. It can feel really overwhelming sometimes, but this is an example of like why it's really important to remember what like all your little reagents and stuff and what they do, and just being able to like quickly look at them, to just see that like, okay, we've got, this is going to cleave that. This is basic condition. We're going to open it up here, right? And then we're going to have our acid workup step to make this the alcohol, right? It can feel a little overwhelming though when you first are looking at it. You're like, what the heck is going on, right? Especially when you like get into mechanisms, it does make it a little bit more confusing. And I know like when it comes to like triple bonds and stuff, I always end up screwing up my drawings because they're not as like nice as your like line angle structures. It's like, wait, this is a triple bond, which means there's like absolutely no rotation around this bond until we get here. So it can feel like a little hard when the drawings are messed up too. So but yeah, just that this definitely is like the biggest like suggestion that I have is just like reviewing your reagents, and just being able to say like, oh, this does this to that, that's like probably the single most thing that would be the most useful. Okay, so this is asking you, it's giving you the reactants and the products, and the rate is giving you everything, and it's just asking you for curved arrow pushing. These are kind of nice. Even like this one's like a little bit long, but these are kind of nice because you kind of know where you're going with it, as opposed to like retrosynthesis. You're like, just make something up, and you're like, oh, good, So what happens first?
Nation.
Go ahead.
Hi. Sorry, say that again. So, okay, so we have two spots where the bond can break, right? So, and this is excess, so we're gonna do them both. So there's this one here, we'll call this A, and let me do it in green here. We've got this one here, and we'll call this B, okay? Now, what do you guys remember about, and so, if we're breaking this, so there's gonna be this carbon here that we're doing, hey, let him go. And so there's this, it's okay, Daddy will come and get him, it's fine. So there's these two carbons here. It's fine, I'm not on camera. So when you're doing these mechanisms, what do you remember about what would go first? Like, how do you know which mechanism is gonna come first?
B because it's least substituted.
Yeah, because you're always gonna do the SN2 first, right? And SN2 does not happen on a tertiary carbon, right? So SN2 will happen first. SN2 is going to happen on B. Okay, so we have, let me just draw, I'm just gonna draw it from the beginning. Okay, so here's this. I always do that. Oh, one day I'll learn, right? Okay, HBr, right? So we do the SN2 first. So I'm gonna take this here, take that there. Okay, and then what's gonna happen is then this becomes, I did it again. Oh gosh, I'll never learn. Okay, and OH, right? Which is positive. And so then this will break off. And our BR will come on at the same time. Right. So this will attack over here. And this is our SN2 reaction, right? And then so what we end up getting is let me see. Count your carbons. OH, and then okay. Have I lost any carbons yet? I don't think so. Okay, and then here we are back to that excess, right? So HBr again. And we're making this a good leaving group. Okay. So we make this a good leaving group. Boop, boop, boop. BR. This is OH. Okay. So this is a good leaving group. Oh, let's not forget our methyls or dimethyls, right? There we go. Pop that bad boy off. That's our SN1 reaction to get our carbocation. Well, it's our setup to our SN1 reaction to get our carbocation. VR. And then, oh, no. Hello. There, that's our cation, right? And then, whoops. And then we've got our bromine. And we attach it here. That's the SN1 reaction, right? And that's how we end up with plus H2O, right? Because this, right? There's our H2O. How are we feeling about that?
I got that one.
Good on that one, yeah.
Cool. Oop. Okay. What do we think about this one? Jackie, you've been pretty quiet. Are you following along? Are you feeling good? Are you listening in the background? Okay. Okay.
It's okay. Don't worry about me. I'm fine.
Okay. I'm worried about you. I haven't heard much from you. Oh, you're funny. All right. How are we feeling about this one? What do you guys think?
Let's do it.
Yeah, let's do it. Okay, so then I know, right? So this is, let me see, give the synthesis reaction. Oh, the target for your target structure. Yeah. So give a synthesis for the target structure on the right from the starting structure on the left. Show all important synthetic intermediates. Do not show any arrow pushing mechanisms. So those are nice, right? It's a break. So what do you guys think? This one's actually, it's not too bad. So, but what do you guys think?
You have to make the epoxide first with the MCP, whatever.
Whoops.
She gives us a list too, which is really nice of like all of the reactions.
Literally, when I saw that, I was like, okay, you
But
guys
yeah,
are
like,
lucky.
I feel like half the time with Pilates class, like I was just like
Oh my gosh.
making
Yeah.
shit up. Like,
Yeah.
oh, I think this is it. And it's writing really badly, so the TAs couldn't read if it was wrong or not.
Yeah. Okay. That's funny. Okay, so we're making our epoxide obviously on the alkene, from the alkene, right? So then what?
You have to break it with OETH.
Yep.
And then the methyl.
Is this gonna be are you gonna do a basic or an acidic? What do you think? Like, are you gonna do, so you're gonna put an OET on it, right?
Yeah.
So is that where is the OET? Trying to think of how I was trying to ask this.
In the OETH or
That, but what I'm saying is like between the two different carbons that this epoxide is attached to, where is the OET attached?
The least substituted carbon.
Yeah, exactly. So the least substituted carbon is the one that gets the nucleophile, right?
Yeah.
Yeah. So we have our OET. This is a T and not a plus sign. This, on the other hand, is a plus and a minus, right? And then what do we do to get the OH?
H3O plus
Uh,
or no, because acidic.
yeah.
Would the OETH work there?
OETH. Oh, yeah, like ETOH, you mean?
Yeah, sorry.
Yeah, no, that's okay. I was like trying to figure out. Yes, exactly. So you'd have your ETOH. Yeah. So you have your basic, right? Because you're putting the OET on the least substituted, right? So so yeah, this one's not that bad. This one's not like terrible. You know, you make your epoxide and then you've got to choose your you know that this has got to be basic, right? So you have to have this, and then you know got to have your OET in there, right? And there's no curved arrow, so we don't have to do mechanism, so this synthesis is like a little bit simpler for the epoxides. I didn't love the epoxides chapter, I'm not gonna lie, but it is what it is. Okay, how are we feeling? Because that's the end of what I have for review for epoxides and ethers. So next I just have the cycloaddition, which I actually really enjoyed cycloaddition. But how are you guys feeling about that last chapter? Besides
Fine.
the like synthesis stuff. Right?
Wait, sorry. For the last one, wait, so yeah, for the ETOH part,
Yes.
how do you know that that's gonna, I mean, I know that like the OET has to go on the least substituted, but then how do you know that like that reagent would make the addition on the most substituted? Like, is that just because the only option left, or?
Yeah, so you're already using, like, OET is already your, right? so this is your, this is your, what am I trying to say? Molecule, I guess, I don't know. This is your, what you're adding to this, and because it
Oh.
has to be a basic condition, remember
Yeah,
that
how do you
when
know wait, how do you know it has to be a basic condition?
because you're adding your OET to the least substituted.
Oh, yeah, okay.
Yeah, so this
Okay.
is your, so this one is your least substituted. So as you're moving through, you see that like your least substitute is getting your product, your reagent, right? Whatever it is. So that's how you know. And so remember that when you have, you know, acidic or basic conditions, you're basically, you know, moving back and forth between, well, this would have a negative on here, right? But OET, right? And you're right, and then so you're sorry, squished, right? But so you're moving back and forth between this in these basic conditions. So you've got this basic condition to get your, this is what goes on here, and then now imagine this exact same thing, but it just has the hydrogen on it, right? Your proton on it, and that's what's going to protonate over here in your basic condition. These are one and the same. The only thing is like whatever side of the equilibrium it's on, right? So that's why you're choosing ET with your OH. And this just stabilizes your
I
anion.
think I think one of the other people mentioned this, but then sorry, I may have missed it. Can you just explain though how you know that you're not using the like the water and stuff? Like, because can't that have the same effect of making an alcohol?
H3O plus, mean?
Um,
or H2O. Well, the thing is when you
yeah,
have water, yeah, go
yeah.
ahead. Okay.
No, like in the example above one of the other ones, like water was added and then a second water was added and you ended with an alcohol in the yeah, in the one
This
in
one
the
up
blue
here.
yeah.
Yeah, so this is so first you're making so this is in an acidic condition. So this is literally an
Okay.
acidic condition, right? Like H3O
Yes.
plus is acidic. But what you end up doing is remember that again, right? Like you're just moving back and forth between these two, depending on what side of the equilibrium is on. Remember that, especially when you're in an aqueous solution, H2O is just everywhere by the trillions and trillions and trillions. And so one peels off, one protonates, another one deprotonates, and then that same one reprotonates. And you know, it's just like a whole cluster of protonations and deprotonations, right? Anything that will happen can happen will, right? When it comes to like chemistry, right? So that's why we try to like control the conditions to try to you know, control the pathway, right? So that's what we're doing here. We're using this to protonate, and then we're adding the OH, right? We're adding because this is going to then, you know, we've got strain, it's an anti-addition, you know, we put this OH on here, and then this water deprotonates over here, the water that's attached to that carbon, and that's how you end up. So we've got a protonation and then a deprotonation, protonation, addition, deprotonation, right?
Okay.
There's one of the chapters, I forgot what it is, but it's like literally 10 steps in one synthesis that's literally just moving protons around. You're protonating this thing, deprotonating that one, protonating this one, deprotonating. It's like just goes back and forth, back and forth, back and forth for like, I'm not even joking, like 10 or 15 steps. So you will, I don't know if you have seen that already. I forget where it is, but it's coming up if it hasn't come yet.
Okay.
So this one literally has to do with like basic condition. Or I mean, this one's acidic condition and this one's basic, right? Because we're adding that OET versus like this. Well, this is predict the product, so that's why it turns out to be just some alcohols. But if we had like ET, but like this one, right? We have the OME that adds on, right? So this is literally that. This whole thing right here is literally this. It's just with ET instead of ME.
Okay.
So it's that same thing, right? So look at this, look at this, NaOET, ETOH, NaOMe, MEOH, because it's a basic.
Got it. All right, thank you for going
Yeah.
over that.
Yeah, of course, absolutely. Any
Also,
other
like, I don't know
questions?
if it's helpful or not, but like it confused me a lot for a while. Like ET and ME is just methyl and ethyl, so they're like literally the same. So you can
Yeah,
interchange them. But like in my head for some reason I thought that they were like their own
methyl and
thing.
ethyl.
Yeah.
Yeah,
So when it's written out just like ME or ET, it's just like the same thing. Like the reagents will be like the same pretty much.
yeah. Right, and then CH2, CH3. This
Yeah.
is, I did this wrong. Right. This is technically like that. There you go.
Like I hate when they like write stuff like sometimes it's like ET, it's like a little thing with like an ET, or it's like the two little things. Like we could just pick one way to write all this, it'd be
Yeah. Yeah. I know. Yeah. Methyl versus ethyl. Yeah. Cool. So far so good. So now here we go. Cycloaddition, right? These ones are kind of fun. I kind of like these. Okay. So how are we feeling about this mechanism? Choosing thermodynamic versus kinetic. What do you guys think?
I didn't see any of this in the thing yet. I only got through like the first two
Got it.
in the homework, but there was like hold on. I mean, you guys can go through whatever you want, but like it's if you're trying to go in the same order, I don't know if this might be one of the ones that she's having a skip because it started with resonance and conjugated systems, and then it went into like the Diels-Alder reactions.
Yep.
Is that
Yep. I have that stuff down here too.
okay? So yeah, because I know that there's a bunch. Yeah, that's like more that look. There's a bunch that she said to skip, so I didn't know like
Got it. Okay. Is this one of them then? Let me see.
I
Let me
haven't
just,
seen that before. That's why I like I'm already having a hard time retaining stuff, so I don't want to retain more than I have to.
no, yeah, absolutely. Do you remember, is it in the announcements that she sent out? Content changes, that one, right? Let's see. Conjugated systems. Oh, kinetic versus dynamic thermodynamic control. Oh, that's too bad. That's kind of a fun one, but okay. We will
That
not be
one?
covering. Okay, so you guys aren't covering this. This is kind of fun, but okay, I get it. You guys are crunched for time. Okay, don't worry about it. I'm glad you said that.
Yeah, I was like, what the hell? I did not see that yet.
Yeah, no, these are fun, but okay, that's okay. And
Yeah,
really,
because
it just has to do with like resonance and like what's your most stable anion versus what's your most or cation versus what's your most stable alkene at the end or stable product. And so that's what that has to do with. But anyway, either way, neither here nor there. How are you guys feeling about these diene and dienophiles? What do you guys think?
these were pretty easy for
Yeah.
me, except for like the third one when they're like a different shape is a little weird sometimes.
Bye, baby. Bye, baby. Yeah, when they're like differently like you mean when they're like in versus out? Is that what you mean?
No, how like that one's like a pentane or whatever instead of like six.
Yeah, I get what you mean. Okay, yeah. Well, we'll go over that. I understand what you're saying. Yeah, because then you start like your product looks like funky, but yeah. There's some like okay. So we'll start up here at the top. Anybody else have any input on how they're feeling? Jackie or Norman?
I actually haven't gotten to that part in the homework yet. I just started the homework today. I was going over all the lectures, and before we got on this, we were just reviewing.
Yeah, no, for sure. That's good. Okay, cool. Well, I'll try to show you some tips and tricks to think about as you're doing them. Okay, so you basically you want to draw like something that's like helpful, right? Is to like I just did here, right? These dotted lines that show where your bonds are going to be between your diene and your dienophile. And then just start with your double bond and draw your arrows moving in the direction. So like we have a double bond here and we have nothing here, right? With these dots. So we're going to draw, and you could draw it in this direction too if you wanted, right? But just choose a direction, just choose something that you do and stick with it, right? So anyway, so we draw that, so that goes there, then this one goes here, and then this one goes here, right? So that's how we know where, and so then this is going to be a 1, 2, 3, 4, 5, 6, right? So we're going to have the pentane, and then our double bond is going to end up there. We've got the methyl here, right? And then we have these there. Okay, so right, inside or outside. So okay, let me back up just a little bit, right? Okay, so we have both of these on wedge, right? But I mean, I know you said that you haven't gone through these, but does anybody know why they're both wedged or they're both dashed, or if they're not, which ones they are, right? But
Yeah, because they're pointing outside of the circle, right? So that they're facing the same way. So like the second one, since they're both pointing out, they would be the same. And then if they're pointing in, it would be the same. Or is that?
yeah, like yeah, so if one was in and one was out, like we see over here, right, with the stain of what we have,
Yeah.
these are both to the right, we could say, right? So these are both to, like if we're looking at like a line here, these two are both to these substituents are both to the right, so they're going to stay on the same side. Yeah, exactly. So yeah, and then depending on the way that it connected, they could either both be wedged or both be dashed, right? So we have this racemic mixture, and so if it's a racemic mixture, it means it is what?
Not optically active.
Yeah. Yep. Optically inactive.
So
Great.
for the second one, since it's both of them are out, but one is up and one is down on the dienophile, I don't know, whatever the one with the two bonds is.
Yep, this is
Okay.
the diene, and these are the
Okay.
dienophiles.
So on the diene, since they're up and like they're both out, are they both like would they both be dashes? Or is it because one's up and one is down? One is dash and one's wedge.
No, so on your diene, it has to do with inside or outside.
So it's the same thing. So since they're okay. I just get these really confused with the chair
Yes.
things.
I know, I
Like,
know.
and then I
I
forget missing
don't
stuff.
have. Oh no, we'll get there where we see, but like let's just take this for example. If we had this,
Yeah, okay, that's what I thought. That's what I thought, but I
yeah. So
didn't.
this is if we draw a line here.
Then that one would be like the top one's a dash and the bottom's a wedge or something.
Yeah,
Or
exactly. As long as they're opposite, yes. But this
okay,
would be considered out, and this would be considered in, right?
okay.
So that would be the difference there, and we'll see that as we kind of move further along here. But yeah. So anyway, so yes. So and it's the same thing, right? So we just draw our cyclohexane, we add our double bond, and then because these are on this what's considered the same side, they're both out, they're both going to have the same, doesn't matter if you choose wedge or dash, and because these are on the same side, right, if we draw a line here, they're both on the right side, right? So that means that they also are going to be on the same side, right? And then this is,
So they're all wedged because they're all out.
yes, they're all out, exactly. Yep. So what do we think about this structure? Optically active, not active, what do you think?
What makes it optically active or not?
The structure. So if it's
Oh,
like,
it's optically active because it has like you can fold it in half. Is that what it is? Is that
yeah, yep. So what
okay.
is it called when it's like this?
So
Uh,
meso?
Yes, miso. So it's optically active, right?
remember we were talking about that earlier, and I was like, I cannot
Right.
remember that, but when you do the little lines, it
Yeah. If basically if it's a mirror image of itself, then it's miso. If it has what's it called? Not congruency. equal reflections. I can't think of the word right now, but anyway, yeah. Then it's meso, which makes it optically active. If it's this racemic mixture, right? Let me write racemic here. If it's a racemic mixture, then it's optically inactive. Cool. So what about this one? What do we think?
Okay, so this is the one with the weird little thingies, and I vaguely remember
Looks like the one
there
that's
being weird ones where like it was like the 6 ring with like another ring inside of it. Is that one of these ones?
Yeah, so yeah, you are gonna have like this other kind of like ring structure going on here, but the theory is all the same, right? We are trying to make a bond from these carbons to these carbons, right? So you just have to like make a decision on where those bonds are trying to form. So regardless of anything else, that's where these bonds are trying to form. So then we just draw, let's see, we're drawing 1, 2, and then 3, 4, and then 5 and 6, and then we just have this little bit in here, right? That's it. Nothing
Well,
crazy. Draw your outside first, which is this right here. 1, 2, 3, 4, 5, 6. That's this, right?
Mm.
5, 6,
Okay.
right? Whoops, that one wasn't straight, but hopefully you guys knew what I was talking about. And then here's our little extra. And we just draw it here. That's it. Nothing crazy, right? Don't worry about what's going on in the middle until you get the base structure down. And then you can like add in your other pieces. Right? So that way you don't overcomplicate it. And then what about our carboxylic acids? What are we doing with these?
One is, oh,
one
go ahead.
dash. I'm just guessing.
No, I did. Sorry, no, you're good. Go ahead. What'd you say? I didn't hear you.
One wedge, one dashed.
Yeah, exactly. Does it matter?
Yes.
No.
No.
As long as you pick one.
They're,
Okay.
yeah, because you can flip them since they're opposites.
Okay.
So then this one would be a racemic, right? Not
Yeah,
optically active?
Yep. Racemic.
Okay.
Yep, exactly. Yeah, no, it's arbitrary, but then once you choose something for a structure, then it's no longer arbitrary for that structure. But initially, yes, wedge and dash is arbitrary, just as long as you stick with that throughout that structure. And then you can change it again on your next structure, unless you're, of course, you're doing some sort of synthesis problem where you have to show multiple structures and you want to keep some consistency for that. But you get what I'm saying.
Okay.
Okay, so now we're ending with the product, which if we see this, what do we know?
They can go both ways.
Yeah, which means
It's,
Racemic.
yeah.
which means
Inactive.
Not.
yeah, exactly. So we've answered that question, right? That was one of the questions. So we've answered that. So now what do we do? So what are we saying? So let's just move backwards, right? So we're gonna move backwards from the same thing that we've been doing here with these arrows. We're just gonna go the opposite way, right? So we're gonna put our double bond here. We're gonna break this bond here, and we're gonna put our double bond here back, right? So now we've at least got a base structure at the very least, right? So we've got this base structure here, and then we've got this base structure here. Now what?
One CN is like facing out and the other one's in. So like it's like an S.
Yeah, like an S. Yeah, exactly. And something that might be helpful to say or think about is like, when you're dealing with like dienes, having like in and out, and then with your dienophiles, left and right. So that might be something that might be helpful to think about as well, is just, are they pointing like in the opposite direction on your dienophile? If they're pointing in the opposite, for your diene, you know what I'm saying? So like because sometimes it can feel confusing, like, is this in or is this out? Like, is this out or is this in? Is this, and so it can start to get a little bit confusing. So maybe with your like smaller, your dyno file is thinking about like if they're pointed in the same direction or if they're pointed in opposite directions. Does that make sense?
Yeah.
Hopefully maybe that'll be helpful. If not, I'm sorry. Okay, so yeah, so exactly. I'm just trying to get rid of these purples. Perfect. So yeah, do I do anything to this, or is this one done?
Sounds good, right?
Yeah, exactly. Perfect. And then just for wholeness, right? We can also have it like this, right? So it could also be like this, but just pick one or the other, right? So these are equally the same. Okay. What do we feel? How do we feel about this one?
Okay, so that one is the same thing, except for the diene has an ET going up and then one going in, like one out, one in.
Yeah, so let me,
Otherwise, it's the same structure.
I'm gonna draw my base.
Does
right?
it matter though if like this, so if you draw it the same way, does the top of the diene have to be the one that's going in because the CN is going up?
Yeah, exactly. Yes. Let me make sure I am, so we have one going out, right?
Yeah.
Whoops. And one going in.
Yep.
And so that means for our Dieno file that which one needs to go to the left or inward towards the circle?
The top one.
Yeah, exactly. And then that makes the bottom one to the
Going out.
right, to the left. Yeah,
Yeah.
okay, cool. Cool, yes,
So
exactly.
even though like they're the same thing, you could just flip them around and they could, when we do the,
Yeah, so you could
Probably
also
right
you could also draw the structure like this.
okay, so we'd have to draw both of them the opposite though.
Yes, exactly. Yep. Did I do that right? In, yeah, I think so. Yeah. Yes, I did that right. Okay. Sometimes it can be a little confusing, right? But yeah. So yes, inward towards the circle, to the left, outwards away from the circle, out away from the circle, to the right, right? And then this is into the circle, this is out of the circle, right? Because eventually you would have this, structure, right?
Yeah.
So yes. Yes to all that. How Norman and Jackie, how are you guys feeling about these?
I think I get it.
Cool. Yeah, this
Yeah,
cycloaddition chapters felt pretty good. Yeah, go ahead.
No, I was gonna say like, I'm glad you explained the like consistency piece with the wedge and dashes because that went over me.
Yeah. I know. There's all those little. I know.
Also, sorry guys for being like annoying with the questions. I just like want to make sure that like I don't.
Yeah, please no.
No, it actually is helpful. Normally that's me.
Yeah, no, you're good. Don't worry. Okay, so talk to me about this one. What's going on with this
Okay.
one?
So this one, there's one of the problems in the homework that screwed me up really bad because
Good.
they had it drawn like this, and I drew some weird shape. But then in the
Mhm.
homework, they like turned the bottom ones.
Mm-hmm. What do you mean turn the bottom ones?
Let me see if I can pull it up because I was like very confused.
So there's a reason this is something to think about, right?
Here,
So
can I show you my screen actually real quick? Just because
Yeah,
like it is
please,
a
go
little
ahead.
bit different, and this is like the one that like
Yeah.
fucked me up bad. It was this. Look, so they had this like that, how that one was, but then they just like twisted it and then made it work.
Yeah. Mm-hmm.
Okay.
Yeah, it's called flipping it. Mm-hmm.
So I thought you couldn't do that because they have to face like the different ways. Oh, you can share your screen again, sorry.
Yeah, no, you're good. I am working on it. It takes me a second because I gotta do multiple things. This one. Okay. Yeah.
You can do that because it's just a single bond, right?
Yes, you can rotate a single bond will rotate 360 degrees. Yes.
Isn't that what they're doing? Or is there something else I'm overlooking?
Yeah, I don't,
So why would you need to flip it? You guys remember what you can't have?
I mean, I don't know if this is the answer, but just in general, don't you flip it to like reduce electron repulsion?
Yeah, remember our chairs? Remember our
Yeah.
chairs? Oh God. No, wait. Sorry. I do this every time, right? What are you doing? Okay. Eh. Okay. Remember your chairs, right? 1, 3, right? You don't want whatever. Let's just say here and here, right? And this CF3. Ah, too much going on.
I hated the chairs, so like good luck.
Yeah. No. I am saying that like these two, like a 1 and 3 structure is no bueno, which is what happens here, right? That's what happens here. 1, 2, 3. Right? 1, 2, 3. And if we have an ET here and a CF3 here, there's a lot of hindrance going on. So what do we do to prevent that from happening, right? What is acceptable? So we can't have 1, 3, but what can we have?
Would you just turn the CF3?
Yeah, you can have a 1, 4, right? So this product, you just flip it over. There, now look at that. So now you can make the attack, right? You can do your thing, which I'm gonna draw this ridiculous thing here, but right, right? Imagine, right? So now we have this on. So that's 1, 2, and then this is carbon 3 and carbon 4, which we're allowed, right? So that means that what we would end up having, excuse me, is we would have our ETOs, we have our methyl, this is our double bond here, right? And then we just flipped our, well, is this, before I get too far, tell me about this and tell me about this. Wedge dash, what do we think?
Which one?
Either of these, the methyl or the CF3. Are they supposed to be wedge dash? What do you think?
Wouldn't the CF3 be wedged because it's pointing out?
Yeah, and what about the other one?
And then that one would be also?
Yep, exactly.
And then the ETOH is just by itself.
Yep, because it didn't change any. It's just it's in line. Like it didn't see how its hybridization didn't change, so it's just on that planar. Yeah, it's just on that planar. But this hybridization did change. So, but yeah, so we just have to flip it around so that way we have these big old. Remember way back in our chair conformations and stuff, like a 1, 3 conformation is like avoided at all costs because of the steric hindrance, the electron repulsion, all of that. So when you're doing these, that's why I put this on here, because I wanted to make sure that you guys saw this, is like when you're doing them, double check that you're not just mindlessly going, okay, this goes here and this goes here, and then what we end up having is we have this, you know, C whatever it is, CF3 and ETOH, right? Because then
Yeah.
you would have a 1 and a 3. Warning, warning, right? So when you have those big substituents, those big groups, they want to be on opposite ends. Okay. So that's what they're doing in that homework problem. They're flipping it around so that way you can have the attachment at a less, you know, less energy, less electron repulsion, steric hindrance, all that stuff, right? Makes sense? How are you feeling?
Yeah. Oh, okay, but hold on, go back up real quick.
Yep.
The homework one though had a double bond O on it. And then
Yep.
it just made it into like two little,
Show me the homework problem again.
it's what?
Just show me the homework problem again. Sorry, I was yawning.
Oh, you're good.
Sorry about that. Let me look at it.
So it had this, so we just ignore
Yeah,
this and keep it
so
on, and then this
so
just stays.
yeah, so where you're attaching it is to, yeah, so they're having you turn this so that way you have your double bonds. Oh, so the reason why they're having you turn this is because you, it doesn't have to do with the 1-3, it's because you need the double bond to create the bond between where like the hydrogen, see how the hydrogen are over there on the right, those two green hydrogen?
Yeah.
If you turned that red structure without rotating around that double or around that single bond where the blue arrow is, what you would end up having is you would have the double bond on top that has the methyl attached to it, and then you would have a single bond, just a sigma there. And it
Oh, I
can't,
see it. Okay.
yeah, so you wouldn't be able to do a cycloaddition because you don't have the pi bond to make the reaction with. That's why that one's doing that.
Okay. And
You
then
actually have to turn the
rest of-
molecule around. Yeah, and the rest of it just stays as it is. It's not
Okay,
really doing
that's
anything.
okay.
Yeah,
Okay.
yeah.
Sorry.
Okay. No, it's fine. I'm glad you asked. I didn't look at all the details of it, so I'm glad you said something. Okay, this one. Okay, here we go. All right. Okay, how are we feeling about these ones? Tell me you've seen this stuff.
I've seen it last time I took the class, but
Okay.
Yeah,
I was-
what are we closing it with?
Yeah, with itself. Okay. So I know it's funny. So I'm going to write this little chart that's super helpful. Let me make more space for myself. Classic me.
Oh, I vaguely remember this.
Oh my goodness, what is going on? Okay, there we go. Right? So N0, 1, 2, 3, right? So if we have 4N, be 0. If we have 4N plus 2, this would be 2. If we have 1N, right, then this would be 4, right? This would be 6. If we have 2, this would be 8. And this would be 10. And if we have 3, this would be 12, etc. Right? So I'm just creating a pattern for you. So when you have 4N, N is the number of electrons that participate in the reaction, in the cycloaddition, or whatever it is that you're doing here, right? This is conrotatory, right? It means that it moves in the same direction. And then if it's 4N plus 2, it means it's disrotatory, right? It means that they move in the opposite direction. And then just a side note, as when we get there, anything that is conrotatory is an SS, a supra, intra-supra, and then this is, whoops, this is supra-supra or intra-intra, right? But we'll get there, but I'm just writing this on here so we have it as something to look back to. So in this case, if you have this, it says for the following electrocyclic ring closures, ring closure reaction, give the curved arrow pushing and the major product of the reaction, right? So we're just doing a ring closure. So we want to close this ring. So what ends up happening, again, we want to close this ring off, okay? So move your electrons to the space in which it needs to be. And then this will go here because it gets pushed out the way, right? And then so what we end up having is how many like carbons are in the circle?
4.
Yeah, exactly. So you have a square and you have your double bond here. And then now tell me about these methyls. Okay,
Are they on
so sorry, go ahead.
the opposite side of the square, but they're both like wedged?
So this is where when we get into our ring closures, remember it's not quite the same as our dienophiles. So we have this con-rotatory and dis-rotatory stuff, right?
One
So
is wedged, one is dashed.
yeah, exactly. How many electrons are participating in this ring closure?
4.
4. So is it a con-rotatory or is it a dis-rotatory?
Con.
Rotatory.
Or dis, sorry.
No,
Con.
no. Whoops, sorry.
Yeah, con.
Yep, con. Yep, we have a con-rotatory, right? So because we have, sorry, I was trying to get my, there, right? 4 electrons that are participating. So it's con-rotatory. So what does con-rotatory mean? That they move in the same direction, right? So these methyls are going to move in the same direction. So if you put your hand out in front of you and you close your fists and you have the back of your hand pointing down and your fingers are on top of your fist, right? And you have your thumbs pointing outward, right? Towards the outsides of the room, like away from each other. And you have a con-rotatory ring closure, that means that they're going to move in the same direction. They can either both move clockwise or they can both move counterclockwise, up to you. But if they move in the same direction, which way are they pointing?
One's
Move them,
in.
move them 90 degrees.
Yeah, so like one's left and one's right.
Yeah, or one's up and one's down, right?
Yeah.
Because if you're starting so that your thumbs are pointing, your left thumb's pointing to the left and your right thumb's pointing to the right,
Yeah.
and you move them both in the same direction, so you're moving them both in a counterclockwise or both in a clockwise direction, 90 degrees, right? Then you would have one pointing up and one pointing down.
Yeah.
How does everybody feel about that concept so far? Norman, do you feel good about that?
Yes.
Okay, cool. So that's why we have one wedge and one dash. Doesn't matter,
Okay.
arbitrary, just pick one, right? So the number of electrons involved in the reaction, we already said it's 4 electrons. Okay, give a drawing of a representation of the wave function of the conjugated pi system on top of the reactant, right? And so this is where, do y'all remember drawing the, like how you find the HOMO, the LUMO with your nodes? I know, Norman, you said that you hadn't really gotten that far in this, but
I kind of remember it from when I took it before.
oh, that's right. Yeah,
but-
yeah. Okay, cool. Yeah. So first, however many carbons you have participating in the reaction, right? We already decided that we have 4 carbons participating in the reaction, right? So we have, this is our system, right? We have pi 1, pi 2, pi 3, pi 4, right? Increasing energy, right, as we go. Okay, and then we said that we have 4 electrons participating in the reaction. So 1, 2, 3, 4, right? So, and the number of nodes that you have, it starts 0 for 2 for pi 1, right, or 2 electrons, right? And then just 1, 2, 3 as you go, right? And you can continue on, right? But this tells you how many nodes are in your conjugated pi system, right? So this is number of carbons or atoms or whatever that are participating in this reaction. For this one, we have a carbon here and a carbon here, here and here, right? Those are the ones that are their pi bonds are participating in this reaction, right? And we have 4 electrons, right? 2 here and 2 here. And so that's why we've filled it in like this, right? And so HOMO is our highest occupied molecular orbital, and LUMO is our lowest unoccupied molecular orbital, right? So in this case, it's asking for, it wants you to draw the pi bond conjugated system on top of this, right? So this is all you will do. So if we have, if our HOMO is on pi 2, how many nodes will we have? One node, exactly. And your nodes always have to evenly split your molecule, right? So the nodes can be either between atoms or they can also run directly on top of an atom. So in this case, because we just have one, it's just going to split it in half. And so all that means is that on one side and on the other side, right? So we have opposite. So a node, remember, it flips where your bonding and anti-bonding systems are, right? Your electron systems, right? So that's all that's asking for, okay? And then number of nodes, we already decided. And for the HOMO, right? This is specifically asking for the HOMO. So we're drawing the HOMO. It asked us to draw the HOMO. So number of nodes, we decided that's 1. So does the allowed reaction proceed by disrotatory or conrotatory? Well, we already decided that it was conrotatory because there are 4 electrons that participate in the reaction, right? How's that feel?
I think it's, yeah, I think I got it.
We got more practice, okay? Any questions on that one so far?
I think where I understand that part. I think where I got confused before is that it continues on and asking again about conrotating and disrotating, like at a different step, I guess. And I think at a different step it changes. And I think, yeah, like right there.
Like in this one?
I think that might be one.
There are some where, well, let's just keep going and let's see, and you tell me if we're hitting any of these, right? So electrocyclic ring closure.
Can you
yeah, go ahead.
Open our homework and work on them from our homework? Maybe?
I can also do that, but for the sake of what's been requested for right now, I just want to finish these as Dr. Pillai had them. I'm happy to do that with you afterwards, but just because I'm recording, I just want to make sure that we're like running through Dr. Pillai's review, and then we can do it afterwards. Yes. And there's only a couple pages left, so we're almost done. Like this is the end of it. So okay, so with this one, so curved arrow pushing for the major products for the reaction, right? So we're trying to close the ring. So that means that we need to, you know, it's not, whoops. It's not going to, why do you keep doing that? It's not going to go to here. Why? It's not going to go to here. There we go. It's not going to go to here because there's nowhere for the electrons to keep going, correct? Right? Do we see that? It has to go to here because the electrons need to be pushed around, right?
Yeah.
Okay, cool. So if we do that, that's the curved arrow pushing is what we see. So then how many carbons are going to be in this ring?
4 again?
4 again, yep. And then, so we're always going to have this double bond here, okay? And then now we have one pointing in and one pointing out, right? We have a methyl here pointing in and a methyl here pointing out. And how many electrons are involved in the reaction?
4. Oh,
Four.
yeah.
4 electrons. Yeah, no, you're right. 4 electrons. Okay. Everybody see that? So if there's 4 electrons in this reaction, is this going to be conrotatory or disrotatory?
on.
Conrotatory, exactly. I'm just going to circle that down there because we're answering these questions as we go. So if it's conrotatory, right, get your fists out with, you'll get your thumbs up out and then just choose, right? For this one, this one on the top, I'm going to represent with my left hand, and this one on the bottom, I'm going to represent with my right hand. So if I have my 2 thumbs up, I'm going to turn my left thumb outward to the left, right? Because it's outside of the ring. And then with my right hand, I'm also going to turn my thumb to the left because it's on the inside of the ring, right? So both of my thumbs are pointed to the left. On my left hand, I have my fingers on top, and on my right hand, I have the back of my hand on top. So far, so good?
Yeah.
Okay, so now we decided that they're conrotatory, so that means that they're going to turn in the same direction. I'm going to choose counterclockwise because my arms are not going to want to turn the other way, right? So if I choose, I mean clockwise. So if I choose to go clockwise, that means that both of my thumbs are moving in the same direction clockwise. What direction will my thumbs be in?
Up.
Yep, both thumbs are going to be pointed up. So what does that mean for my drawing?
They're both dashed or both wedged.
Exactly. Yep, exactly. Right? So far, so good. So if this is a racemic mixture, what does that mean?
It's not actively active.
Yeah, right? So far, so good. Okay. So now give a drawing of the representation of the wave function for the HOMO of the conjugated pi system on top of the reactant, right? So we're just going to go back to doing that same thing. We decided that there are 4 carbons that are participating with their pi bonds in this reaction, right? So that's all this is. We're just, how many pi systems are participating, right? So there's 4 systems. 1, 2, 3, 4. Okay. And we have 4 electrons. So we'll just fill them in. And so where's the HOMO? Where's the LUMO?
The HOMO is number pi 2, and then the LUMO is pi 3.
Exactly. Yep. Exactly. Because HOMO is the highest occupied and LUMO is the lowest unoccupied, right? Molecular orbital. So how many nodes does the HOMO have?
1.
1 node. Yep, exactly. And then so all we will do, we will choose to put the node there to split the molecule in half. And then I'm just going to add my pi systems on top. And if we have 1 node, we just have 1 flip. Whoops. There, right? Those are pi systems on top of the reactant. So far, so good? Number of nodes we decided is 1. And the allowed reaction, that's the thing, right? Is this reaction allowed or not? Sometimes you will see a picture of a before and a picture of an after, right? A reactant and a product, and then it'll say, is this product allowed or not allowed? And you have to decide, depending on the number of electrons, whether or not it's been disrotatory or conrotatory, how many nodes there is, right? How many nodes there are. If the product is allowed or not, right? So in this case, the allowed reaction, because that's what we just solved for, is conrotatory. We figured that out back up here. Okay. How are we feeling?
Good.
Okay. One more. We'll do one more. Let's see. Okay, so what are we doing here? Right? So we're going to put a bond here, and we're going to start here, and here, and here. Okay, so how many sides is this ring going to have?
6.
Yep. And we'll just put our double bond here. Okay. And then what do we think about our methyls? So we decided there's 6, so we know we have 6 carbons. How many electrons are participating in the reaction in the cyclic, in the electrocyclic ring closure?
Wouldn't it also be 6?
Yes.
Is there only
exactly.
one double bond or is there 2 in the product?
Oh, sorry. Yes, thank you. I did it. I did this. Yes. No, thank you for that. It's here and here. My apologies. Thank you. Always count your carbons, count your sides, count your bonds, right? It's easy to do. Okay, so there's 6 electrons that are participating in this reaction. So is this conrotatory or disrotatory?
Disrotatory.
Disrotatory, right? So
We have that chart, or we just have that memorized.
this is just something that you should know. I don't think you'll get this chart. Conrotatory is 4N and it's the super antra. Disrotatory is 4N plus, because it's just like 4, 8, 12, right? Or 2, 6, 10, 14, So yeah, I don't know. I would say just memorize this the best you can. Like, I'm not gonna lie. Yeah, sorry about that. Yeah, so okay, so disrotatory we've decided, right? So if we have disrotatory, then that means that they are going to move in the opposite direction. So now I'm choosing this to be my left thumb and this to be my right thumb. And because this is inside and this is outside, so with my thumbs up on my left hand, I have my thumb turned to the right, towards the inside of my midline. And on my right thumb, I have my thumb turned also to the right towards the wall, right? So both of my thumbs are pointed to the right. My left hand has the back of my hand on top and my right hand has my fingers on top, okay? So now this is disrotatory, which means that they rotate in the opposite direction. So if they rotate in the opposite direction, if I rotate my left thumb clockwise, it will move which direction, up or down? If I have my left thumb pointing to the right and I want to rotate my hand clockwise, will my thumb be pointing up or down?
Yeah.
Down, exactly. Now my right hand, which also has my thumb pointed to the right, needs to move in the opposite direction, which is counterclockwise. Will my thumb be pointed up or down? Up, exactly. So we've decided that our thumbs will be pointed one up, one down. Right?
Yes.
So that means one wedge, one dash, right?
Which one gets which?
Doesn't matter. Arbitrary. Arbitrary, right? So give the drawing of the representation of the HOMO for the pi system. Okay, so how many pi systems, how many how many carbons, how many pi systems from carbons are in the reaction?
6.
1, 2, 3, 4, 5, 6. By 1, by 2. It's very redundant. I ended up shorthanding a lot of this stuff after a while, but it's good to just go through it, right? And we decided that how many electrons are involved in the reaction?
6.
1, 2, 3, 4, 5, 6. 0. 1, 2, 3, 4, 5, right? So where's the HOMO? Pi what?
Factory.
Yep. Where's the LUMO? Pi 4. Yep. So how many nodes does the HOMO of the conjugated pi system have?
2.
2. Okay. So where are we going to split it? How are we going to split it if we have 2?
Okay,
Between
hold on. Real quick, I'm really confused. So when
That's
you
okay.
drew these and it's homo's the highest occupied one, right?
Yep.
Okay, so on the line number 1 on the bottom, that's 0, that one's occupied.
Mhm.
And then the next line is 1 and that's occupied.
Yeah.
And 3 and that's occupied.
No, this is a 2. It's a 2.
Okay, so
This
2 is
is
occupied,
3.
but
This
you-
is, so don't get this confused. This is number of nodes.
yeah.
This is number of nodes, and this is, pi systems, right?
Yeah, so
Pi
does
sys-
number of
yeah.
nodes go with the homo or the lumo?
This question is specifically asking for the homo.
So would it be 3 then? Because, or 2, because you have 1 is 0, and then the next one up is 1, and the next one up is 2.
Yes. Did he say 3? I thought he said 2.
No, because the last one too, you did it like that too, and I thought I was just drawing it wrong or writing it wrong.
Oh, what do you mean? In this one, yeah, there's 1 node, and I drew 1 node right here.
I know, but
Mm.
when you were saying it, you said like 2 for homo and 3 for lumo, I'm pretty sure.
Oh, I was
Pi
saying
2.
pi 2 and pi
Oh,
3.
okay, yeah, okay, so yeah, so never mind. So then down below, then like
Yeah,
there's
so the homo, so that's what I was saying is like, which pi would the homo be at, right?
oh,
So
okay.
that's why he said pi 3, right? And which pi would the lumo be at? Pi 4, right?
Oh,
This
I
is
thought you
just
were talking about nodes. I'm sorry.
no, and then my follow-up question was how many nodes, right? But I was initially just asking for like what was the pi system that homo was associated with, and that's pi 3.
Okay, sorry.
No, I'm glad you clarified. I'm sure you're not the only person that had that question. So we have 2 nodes, okay? We have 2 nodes, and here's our 6 carbons that are participating, or 6 pi systems that are participating, right? And remember that we have to split it evenly. So let's just say that this is 1, 2, 3, 4, 5, and 6. Where do our 2 nodes go?
Between 2 and 3 and 4 and 5.
Yeah, exactly. Does everybody see that? Does everybody agree with that?
Yeah.
Right? So we make an even cut across the board. So then we'll just draw our pi systems, right? And then, so let's call this A, B, and C. What gets filled in top or bottom for A?
So if you did top for A, you would do bottom for B and then top for C, right?
Mm-hmm. Exactly. And then you could also just do the total opposite, right? Because it's arbitrary until you make a decision. Once you make a decision, it's like Schrodinger's cat. It's like once you open the box, then you've made a decision, right? Does that make sense? So we could also have it so that our pi systems were this, right? And then, this also could have been our pi systems, right? I'm obviously trying to just shorthand it to show you that is also accurate, right? But we chose one, so we're sticking with that one. Everybody feel good?
Yes.
Okay, cool. So we already said number of nodes is 2. Does this allowed reaction, so that means the one that's actually going to happen, does this allowed reaction proceed disrotatory or conrotatory? What did we decide?
It's rotatory.
Yeah, it was disrotatory, right? Because we solved this problem as if it was allowed, right? So that's how we know that it is disrotatory as we did initially up here, right? And we made that decision based on the amount of electrons that were participating in the reaction. Okay? Okay, what do we feel about this? Rank the following structures in order of increasing rate of reaction in the Diels-Alder reaction and give a brief explanation that includes the terms donating group, withdrawing group, energy of electrons, and HOMO, right? So what do we think? What do we think about this?
I have no idea.
Yeah, no idea.
Okay. Yeah. No, you're good. Okay, so
Are
let's
these
start with,
deals Alder reactions, I guess, then?
sorry, say that again?
Are these the deals Alder reactions?
Yeah, so we have this is common between all of them, right? So these are common things here, right? So if you have what is it that you have, like, okay, so our slowest reaction is going to be what? Like, not as far as like A, B, or C, but like when you're looking at these, thinking about these terms, donating group, withdrawing group, energy of electrons, homolumo, whatever, all of those, right? What would be slower between a slower reaction between, let's say, a donating group or a withdrawing group?
Um, I would think
Oh,
one
wait.
is more bulky.
So with, do you guys remember like how to tell the difference between like a withdrawing group or a donating group, or like when you have, let's, like this is what I'm talking, this would be considered your like your group, right? This is your group, this is your group, right? So when you have like withdrawing groups versus donating groups, the best way that I found to memorize these was that if you had in your like conjugated system, right? Say you have, say you have this system here, right? And then you've got some group here. If you have a more electronegative atom closer to the conjugated system, then it will be a donating group, right? It will be a donating group because it will participate in this resonance, right? But if you have a group that has the more electronegative atom on the outside, away from the resonance system, then this will be a withdrawing group because it is pulling the electron density away from this resonance structure. So that is the quick and dirty way to decide if something is a withdrawing group or a donating group. Does that make sense?
Yes.
Okay, yeah. So this, like, for example, this will come on here because it's not being pulled away by a more electronegative, but because this is being pulled away by a more electronegative oxygen over here, the electrons are not going to move in this direction into that resonance, right? So this is the quick and dirty way to decide if something is withdrawing or donating, right? And then of course there's levels to it like everything else. But so knowing what we know now, remembering what we knew before, right? Is this a withdrawing group or is this a donating group? Is A withdrawing group or is it a donating group?
A donating group.
Donating group. Yeah. Is this a withdrawing group? Is B a withdrawing group or a donating group?
A donating group as well.
Well, okay. I understand why you think that, right? It's a little bit of a trick question. Think about it like this, okay? If we have oxygen here, in which direction can these electrons on this green pi bond move? Can they move towards, or will they more likely move away?
Away.
Yeah, which makes it a
Withdrawing.
yes. Does that make sense?
Yes.
Cool. Awesome. So, and then with this one, with C,
Is
you
it withdrawing?
have, well, it's also kind of a donating group because if you think about it, right? If you think about it, this is the next atom away from here, right? So the next atom over is actually less electronegative. So it will donate. So it is a donating group, but it has some like minor resonance contributors because of this can go here and then these can go here. So it's kind of like a half and half, right? Like it can donate, but it also has this kind of this pull from this other oxygen over here, right? So it will still donate, but not as much as say this donating group over here, right? So with that in mind, a withdrawing group or a donating group would be a faster reaction. So if you can give your electrons to participate in a reaction, are you going to react more quickly? Or if you want to keep all the electrons to yourself, are you going to react more quickly? Remember that you need electrons in order to react.
If you can donate them, then you react faster.
Yes, exactly. So we've decided that donating groups will react faster than withdrawing groups. Because we have two kinds of donating groups and one withdrawing group, which one will be the slowest?
The withdrawing group is the slowest.
Right, B, exactly. So then between the two donating groups, as we said before, because there's some minor resonance contributors with C, with this other double bonded O that will, you know, pull the electrons this way, and these will come in and pop over here because this will all of a sudden have a positive charge, right? Even though it will also donate, it's just not going to donate as often or as much as we would see in A. So that's why A would be the fastest. Does that make sense?
Yeah.
Yeah. Cool. Awesome. And then similar in this, rank the following reactions A, B, C in order of increasing exothermicity, right? So what's a conjugated system? We'll start there.
A conjugated system is like you have, isn't it just like the opposite charge? Like if you have a base, you have an acid.
I mean, so yeah, you have like different, right? So it's basically a conjugated system is alternating double single bonds because you get this resonance structure, right? You get this movement of electrons around, say, in this example, a ring, right? So that's what a conjugated system is. So conjugated systems have more stability, right? They have more, and that's kind of sucks that you guys didn't get to do like the kinetic and thermodynamic stuff, because it kind of helps to like see how that's like relates. So I don't know if you'll necessarily even have a question like this, but in that sense, right? Tell me, are A, B, and C the initial products? Are all of them conjugated systems?
No.
Which one is not?
All of them?
Defining.
Oh.
Yeah, B, right? We're defining a conjugated system as alternating single double bonds. So double, I'm just going to change color, single, double, right? Single, right? There's some, it doesn't have to be all the way around, right? The whole system doesn't have to be conjugated.
All the way around.
I get what you're saying now. Yeah, the whole system doesn't have to be conjugated, but there has to be some sort of conjugation, right? So single, double, single, double, right? Whoops. Ooh, single, right? We've got, in this one, we've got a single, we've got a double, we've got a single, and then a single, and then a double, and then a single, okay? So B is not alternating, right? So B does not have any conjugated systems. It does not have resonance structure, which means in this case, if you were moving, so the only thing that's different are your reactants, right? Your reactants are the only thing that's different. Your products are all the same, okay? You guys remember the energy diagrams, right? So you have your products and your reactants, right? So, and then, you know, you move, right? You have your transition state, and maybe you have your intermediate, right? This would be like your intermediate, and this would be transition state 2, right? Number 2. Okay. This is like a very crappy drawing, but just to like, you know, try to refresh your memory here, right? So if all of your products are the same, but your you know, your reactants are different, then we want to find like what's the difference with these reactants, because remember, when we're talking about exothermicity, we're talking about the difference in energy states, the difference in movement, right? From your product to your reactant, or from your reactant to your product, right? So that's what it's talking about with exothermicity, increasing exothermicity. So if you have no resonance, then you don't have anything to stabilize you during your transition states, right? So that means that anything that does not have a conjugated system will have the highest exothermicity, because it's going from here to here. There's nothing in between, right?
Mm-hmm.
Whereas when you start to have these systems here, that's when you have these like drops, right? So this would be the highest exothermicity because there's no conjugated system, right? No conjugation. Okay. Did you guys talk about like substituents on the alkene? I don't know who, like, I know Norman, you said you haven't gotten this far yet in your lectures recently, so this is like kind of getting into the details a little bit. So, so when we're talking about, so first you're going to decide if there's a conjugated system, right? And then the next piece that you'll look at is how substituted are your alkenes, right? And so here we have 1, 2, 3. So we have a hydrogen here. Not that it really matters. This one doesn't count. Sorry. We have a hydrogen here, right? And then we have a hydrogen here and a hydrogen here, right? So we've already decided that this one is the highest because there's no conjugated systems, right? And then for these ones, we have hydrogen here, hydrogen here, hydrogen here, hydrogen here. Remember, we don't count hydrogens for how substituted it is, but it's a good way to see if there's more hydrogens, then that means what? It's more or less substituted. If you see more hydrogens on your alkenes, is it more or less substituted?
Less?
Yeah, less substituted, right? So this is a great way to see if you draw your hydrogens on. If you have less hydrogens, that means it's more substituted. And if it's more substituted, it's more stable, right? So this would have the lowest exothermicity, and this would be in the middle, right? So highest because there's no conjugation, lowest because it's most substituted, aka most stable. And then obviously, if you only have 3 choices, one of them's got to go in the middle. Make sense?
Yes.
Cool. All right, let's just do these reasonable resonance contributors. This is like the last little piece of this. So, yeah, so where would we start? Where would we start on A?
Moving the electrons.
Yeah, but which ones?
The non-bonding.
Yeah, the non-bonding electrons, right? I'm just gonna keep drawing my resonance structures this way. Okay, so if I move these electrons over here, then that would mean that I also have to move what? These electrons here, right? So then we draw our structure again. There's 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. Oh God. If you draw a line, count 2, you know, like when you start off, this is 2 carbons and then 3, 4, 5. Don't go 1, 2, you know, that's what I always end up doing. Just FYI, because I lose my carbons along the way. Okay, so now we have this here. Okay, now what? Oh, whoops. Sorry, let's not forget this. All right. So now we just move those electrons again, right? We just move those non-bonding electrons again. 2, 3, 4, 5. Okay. And then we've got this, and we got that. Is there anything else we can do? You guys see anything else that can happen on this? I don't.
No.
right? So now, indicate the position of many vertical nodes on the wave function, how many electrons are associated in the conjugated system. Okay, so what's our overall resonance structure, right? You guys remember how to draw these? You
With
do
the
your base. Yeah, go ahead.
yes. I'm
No, go
sorry,
ahead.
you just do the dashes through what all the electrons that you're moving.
Yeah,
So just a dotted line along the bottom.
yeah. And because we had electrons moving in all of them, we have this. And then what's the last piece of this? Partial charges, right? Partial negative, partial negative, partial negative. Anywhere that we see non-bonding electrons, we've got to draw as our partial negative. You can also, although this question doesn't ask for it, but you can add 1/3 if you want. It's implied, right? But you can add that if you wanted to, right? So that's your reasonable resonance contributor. Okay, so and then it's asking for the HOMO and the LUMO. So how many pi systems are there?
3,
5.
5. Yeah, yeah, right?
And the top ones, like, they get it too.
Yeah, every single carbon in this structure is associated with a pi system at some point, correct?
Yeah.
So we have 5 pi systems. 1, 2, 3, 4, 5, right? Pi 1, pi 2, pi 3, pi 4, pi 5, right? And then our nodes are like this, okay? And then so how many electrons do we have?
6.
6. 1, 2, 3, 4, 5, 6, right? So which pi system is our HOMO in?
Pi
3.
3.
Yep. And what about our LUMO?
Pi 4.
Yep, exactly. So how many nodes will our HOMO have?
2.
Yep, 2 nodes for a HOMO. And how many will our LUMO have?
3.
3. Yep. Okay, so I'm just going to draw these. Tell me, where would I put, imagine that this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, labeling my carbons. Where would I put for the HOMO? Where would I put the nodes?
On 2 and 4.
On 2. Let me move this. Let me change this color. On 2 and 4. Yep, exactly. So in this case, because we're putting it on there, we wouldn't actually draw these, right? So I drew it all out so you could see it happen, but you would just do this, and then you would draw that your node is here, right? And that's all you would do. You would just, draw it down the middle, right? So then which ones are up and which ones are down? Or which ones are on top, which ones are on bottom?
1 is like up, 3 down, 5 up.
Yep. Does everybody agree with that?
Yes.
Right? So this is not to be confused with this node, right? Those are different. I know they're the same color. So okay, what about our LUMO? How many nodes do we have?
3.
Three nodes. So where are those ones gonna go?
Would it be on 2, 3, 4?
If we did it on 2, 3, 4, are all of the sections equal?
No. No.
Let's try again.
So then 1, 3, 5.
On 1, 3, and 5. Good guess. But you can't really have a node here because there's nothing on this side for it to switch to.
Okay, so that was going to be my question on the HOMO one. Can we have it in between the?
Yeah, of course. You can have, yeah. It can either be on a bond or on an atom or both, right? Like differently, right? As long as it's all equal. So where would we put them?
So then between 1 and 2, 2 and 3, and something like that.
Yeah, so we would do it between 1 and 2. That part is correct. Then we would do it right on 3,
Okay.
and then between 4 and 5. And now notice that in this system, how many pi systems are in each section?
1.
There's 1 pi system in each section, right? I'm going to get rid of this pi system because the node is directly upon it, right? So I'm getting rid of this pi.
But it has to be done evenly.
As long as it's done evenly. So this one is showing, I'm putting a dot there to represent that there's a node. As long as it's done evenly. So now we have 3 nodes where it flips. And each section has an equal distribution, we'll say. Okay. So far, so good.
Yes.
So tell me which ones are up and which ones are down. Which ones are anti, which ones are bonding.
So you could do like 1 up, 2 down,
Mhm.
4 up, 5 down.
Yep. Arbitrary until you pick something, right? Could have been equally bottom, top, bottom, top, right? Yeah. Wait. Yeah. So it could have been either way. So just as long as you pick something, right? How are we feeling about this?
This one seems straightforward.
Cool. And then I should have drawn these in, so I apologize. I was just worried about the backbone, but I should have drawn those in. So just to be complete, because it's asking for the original from the original structure. So, okay, cool. Last one. Second to last one. Well, okay, let's do this. Let's see. We have a positive charge here. Oh, whoops. You know what? I'm just going to use this one. Okay, so what would we do first for this resonance?
Move 1, yeah.
Sorry, say that again.
Move the positive charge.
Can't move a positive charge. You can only move electrons.
So then move the double bonds.
Move the electrons in the pi bond to the cation.
Yes.
Cool. Yeah.
You
And
only
then
move that one because the other one's not that close to it.
yeah, because you're just filling it in. So now we're gonna do it again, right?
Oh, okay.
Yeah. You got to move the charge first before you can move the electron. Right? Anything else we can do?
Move it
No.
down again.
No, we don't have anything else, right? This is an sp3 hybridized, and we've already
Yeah.
moved this here. That's this structure here, right?
Yeah.
So there's nothing else we can do. So that's it. That's our structure. And then our overall resonance structure would be what? And then we would put partial positive, partial positive, partial positive, right? Because we have, as we see, in these areas, right? Okay, so now it's asking for our HOMO and our LUMO. So how many pi systems are reacting?
5.
1, 2, 3, 4, 5. Yep. 1, 2, 3, 4, 5. How many electrons?
6.
How many electrons?
Oh,
4.
4.
Yeah. Yeah. No, see, right? Like we get into this system of like, oh, but we have a cation. So we actually only had 4 electrons. Okay. So how many nodes are in our HOMO?
1,
Yep. And how many nodes are in our LUMO?
2.
Yep. And let me just make sure I'm doing this to completeness the first time before I get ahead of myself. Okay. And then, so we have 5 pi systems. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Great. So we decided we have one node in our HOMO and 2 nodes in our LUMO. Okay, so where should our nodes be?
The middle one on the HOMO, just on top
Yep.
of it. And then on top of 2 and 4 on the LUMO.
Yeah, just like this. Yeah, exactly. And then again, we just choose opposites, right? If this is up, this is down, and this is up, right? And these are nodes. So, you know, you wouldn't necessarily draw that, but you're just representing that that's a node there, right? But I was just drawing it so you guys could see. Okay. Not too bad, not too bad. Okay. This is the last one. This is the last one, I swear. But I think it's important if you guys have to do this stuff that it's important to kind of see with this one. So it says give the arrow pushing for the provided cycloaddition reaction and the number of electrons involved in the reaction. So the curved arrow pushing, right, for this one, where would we start? For like how many electrons are involved in this reaction?
I have no idea.
So we have over here, we have our dienophile, right? And then here we have our diene, right? So how many electrons are going to participate with the dienophile?
2.
2 electrons, exactly. And what about with our diene? How many electrons are going to participate in this reaction?
4.
4, yeah, right? We have a pair here and a pair here, right? So, and what we're trying to do is we're trying to create cycloaddition, okay? So our curved arrow pushing is what? We take these electrons, start with your non-bonding pair of electrons, right? These electrons, and we put them here. And then this pi electrons move here. And then these electrons, right? These ones move here onto this oxygen, right? Because this oxygen has a positive charge, right? Make sense? Okay, cool. So then we draw it out. So how many carbons are in this ring? Or, I'm sorry, how many atoms are in this ring? They're not all carbons.
5.
Yep, 5. 1, 2, 3, 4, 5. Little pentane, right? And then, so with our nitrile up here, our wedge, dash, what's going on?
They're both wedged or both dashed.
Yeah, exactly. Yep, because they're both outside, right? That's all that means. The only reason why they're like that, right? Okay, so now it's asked, so this, I'm not drawing it because CH2, obviously you have your hydrogens here, but just so we know that that's what this is, right? Okay, so optically active or no? And why or why not?
Optically active because it's meso.
Yay, meso, optically active, right? Okay, so so now with this, so now it's asking, so state whether the reaction would be superficial or superficial and trificial, right? So when we're figuring that out, we need to start with our
Would it be superficial because it's 2 or 4n plus 2?
so let's see and see. Okay, so how many pi systems participate in our dienophile up top? I'm going to label this A and B, but this is our dienophile and this is our diene. Okay, so did I do that right? Yeah, this has a plus sign. So how many pi systems are in our dienophile in A?
2.
2 pi systems. How many electrons participate?
2.
2.
How many pi systems are in our diene? are diene like really, but in B, how many pi systems? Yep, 3. Yep. I know it feels a little bit confusing, right? But there is still like 3 that are happening, right? So, and then how many electrons are participating in this cycloaddition? 4. 1, 2, 3, 4. 0, 1, 2, right? These are just our nodes. I'm just doing our nodes. So for simplicity's sake, figuring out what our pi systems are, remember superficial means that you have your bonding or anti-bonding are the same when they're coming together, or superficial antificial means that they're opposite. So they're located oppositely so that you're bonding like from the top to the bottom rather than top to top, right? Because remember, when we think about these in terms of like this, if it's coming in, right, this would be an example of superficial, and this would be an example of antificial, right? So depending on where your bonding versus anti-bonding is on your diene and your dienophiles is what determines, because what ends up happening if you have an antificial, yeah, you'll have your system, right? Say you have your system here, and then you'll have your system. Let me just draw the 2 because it'll just be a little bit easier to see on this 2D picture. So what ends up happening is you have your system coming in like this, as opposed to coming in like this. Does that make sense? So this is your like molecule, this is your atom here. Whoops. So you're coming in like the top of one is connecting to the bottom of another. That's what antificial means, right? So with that being said, there are, for simplicity's sake, there are 0 nodes on this HOMO, right? So we have to connect a HOMO and a LUMO, right? Because we're taking our highest occupied and attaching it to our lowest unoccupied, because we have electrons that we're trying to put into another space, which would be our unoccupied molecular orbital, right? Does that part make sense?
Yeah.
So we want our electrons that we have to go into a space that will accept them. Same thing as like Lewis acid, Lewis base type stuff, right? We have electrons and we want to we want to connect them with somebody else, something else, right? So same idea. So with that being said, if we choose this as our HOMO, again, it doesn't matter, but we like to be simple, right? We like to be lazy. So if we choose this to be our HOMO, then there's 0 nodes and I don't have to do anything. I can just choose arbitrarily whatever ones I want, right? So far, so good?
Yes.
So that means that the other one has to be my LUMO. So, and my LUMO has 2 nodes. So the only place to put 2 nodes to make everything even would be here, right?
Yes.
And so now we have this coming in to this, right? That means that this is antificial because they're opposites, right? Sorry, superficial. They're the same, sorry, same phase, right? So another way to think about it is, because you could, right? You could do this, sorry. This, right? So superficial, they're in the same phase. Oops, I did it again. I did them all opposite. Yes. Okay, there we go. This, okay, perfect. So now, so they're in the same phase, right? So the top, right, is your bonding and the top is your bonding. So that makes this superficial, or antificial, right? So either antra, because they're both non-bonding, or supra, because they're both bonding, right? So when it's asking, state whether the allowed cycloaddition would be supra or supra-antra. Supra-antra would be if one was on bottom and one was on top where they were coming in, right? So in the case of before where I had the bottom filled in and the top not filled in, the point is that there are two of the same that are going to be connecting to two that are the same. So it's arbitrary because I could just flip it around so that both of the the bonding orbitals, right, are both on top, right? So just to clarify why I changed that around. The point is that like the end pi systems are the same, and these end pi systems are also the same. They're not opposite, right? If there was a node here, then they would be opposite. And this would be your bonding, and this would be your non-bonding, and then that would be antra, right? But it's not. There's no node there. Okay, so another way to think about this, like I had said, all the way back up here, is that if you have your electrons, remember that if it's disrotatory, it's going to be supra-supra or antra-antra. So if it's a 4n plus 2 system, which means 2, 6, 10, 14, it's supra-supra, antra-antra, right? If it's a 4n system, 0, 4, 8, right? Then it's supra-antra, right? So we made this decision down here, oh, right here, that we had 6 total electrons participating in the reaction. So we didn't have to go through this whole rigmarole to find that out, but I wanted you guys to see it so that you knew why. But if you want to just cut to the chase and say, this has 6 electrons, so I know it's going to be supra-supra or antra-antra, you're more than welcome to do that.
And it doesn't matter, like, you don't put just supra-supra or antra-antra.
No, I mean, you know, because it's the same thing. If it's antra-antra, then it's supra-supra, you know, so it's like, you know, this is specifically asking, like, is this a supra-supra or a supra-antra, right? So it's asking if it's this or if it's this, right? Supra-antra would be if one was, supra-antra would be if,
No, yeah, no, I know. I didn't know if,
you know,
like,
yeah, no. I guess I always just write supra-supra, but yeah. Sound good?
Yes.
So it, I guess antra-antra would be like if you had this coming in with each other, right? So like these were coming in to like make the bond together, right? Versus supra-supra is when you have this, right? Because supra-supra just means that both of the bonding are on the same side. Like if this is one and this is another system, right? So supra-supra just means that the bonding versus anti-bonding are all on the same side for that pi system, versus antra means that it's opposite bonding, anti-bonding within that pi system. Does that make sense? So that's why you would use antra-antra if your connection came through like this. But this, because we're using this is one system, and then we're using these, this is the other system that's coming in to make that connection, right? So they're both on the same side. They're both on the same side.
Okay.
If they were both on, if, you know, one was opposite and one was opposite, then yes, it would be antra-antra. Does that make sense?
Yeah.
Cool. Any questions so far?
No.
Okay, that's what I have for the review. Danielle, I would be happy to, if you wanted to meet, I know you guys have your stuff on Friday. If you wanted to meet again to go over some homework problems that you have questions on, I'd be happy to do that. You know, and that goes for anybody, if anybody ever wanted to do that. I'd be happy to like go over that type of stuff.